All right, team, listen up. As your chief systems engineer, I've called this briefing because we are about to kick off what is, without a doubt, our most critical mission yet. We are going to build the brain for our next generation micro EV. This is the strategy session. Let's get right to it.
So, the mission is pretty straightforward, but it's a big one. We have to design a world-class motor control unit, the MCU, starting from, well, nothing, a blank sheet of paper. This thing is the nerve center of the car. It's what turns the driver's intention into actual movement. So the big question is, with a challenge this big, where do you even begin?
You don't start with a circuit diagram. You don't start by writing a single line of code. You start with intelligence. See, a winning strategy is never ever built in a vacuum. It begins by systematically taking apart and understanding what the global competition is doing.
And when you look out at that global landscape, you quickly realize it's complicated. The world's major markets have come up with three completely different engineering philosophies for these little EVs. Each one has been shaped by its own unique set of rules, regulations, and what customers actually want.
Okay, first up, Europe. Think of the Citroën Ami. Their philosophy is driven entirely by regulation. The big one is the L6E light quadricycle rule, which clamps power down to just 6 kilowatts. That basically forces you into a 48-volt touch-safe system. Now, it's safe, it's compliant, but its weakness is glaring. At 48 volts, trying to get more power means pumping in huge amounts of current, which leads to massive energy loss. It's a performance dead end.
Now let's pivot to China, the Wuling Hongguang Mini EV. This is a totally different universe. The philosophy here is brutally simple. Cost is king. The market is so competitive, it's produced a masterclass in cost-down engineering. They're using a 96-volt system to get the 20 to 30 kilowatts of power that their customers actually demand, and they're doing it with cheap, off-the-shelf, discrete components. It's incredibly effective.
And then there's Japan. You look at the Toyota C+pod, and you see a philosophy of pure, unadulterated efficiency. They're using surprisingly high voltage, almost 178 volts, for a pretty modest 9.2 kilowatts of power. So why would they do that? Simple physics. High voltage means low current. And low current means you're not wasting energy as heat. It's a direct lesson learned from Toyota's decades of dominating the hybrid space.
So, let's put it all together on one slide. This is the global battlefield. Look at the priorities. Europe, compliance is everything. China, it's all about cost. Japan, it's all about efficiency. These market pressures have literally forged three totally separate technical paths. We absolutely cannot design our system without understanding these three conflicting realities.
So, after analyzing the opposition, it's time to define our strategy. And let me be clear, we are not just copying one region. We're going to forge a strategic compromise that can win globally. And that winning blueprint will be built on a 96-volt platform.
So why 96 volts? Because it is the perfect Goldilocks voltage. It's not too low, not too high. It's got enough punch to deliver up to 30 kilowatts of peak power, which means we can play in everything from the higher-end European L7E class to the Chinese A00 class cars, and maybe most importantly, it lets us tap into the absolutely massive and therefore cost-effective global supply chain for 150-volt MOSFETs. These are the little electronic switches that run the whole show. It's the absolute sweet spot between performance and cost.
And that leads us to our next huge strategic decision. We are saying no to expensive, complex, integrated power modules. Instead, we are all in on using discrete individual MOSFETs, just like the Chinese do. Why? Well, this single choice gives us a lower bill of materials, a way more resilient supply chain. It's easy to scale up by just adding more in parallel, and it's much more redundant. This is a massive strategic win for us.
And when we go to pick those MOSFETs, this number is our non-negotiable target. The on resistance, or R_DS on, has to be less than 3 milliohms. So why are we so obsessed with this one number? Because in power electronics, resistance is the enemy. Resistance equals heat, and heat is just wasted energy. Hitting this ultra-low target is fundamental to building a controller that runs cool, efficient, and reliable.
But look, hardware is only half the story. Our real secret sauce, our true competitive edge, is going to be the software, the soul of our MCU. We're going to implement advanced control algorithms. We're talking field-oriented control, which gives you that incredibly smooth, silent acceleration. We're using max torque per ampere to squeeze every possible meter of range out of the battery during city driving, and we'll use flux weakening to let the motor spin faster and unlock higher top speeds. This is what makes a car feel amazing to drive.
Okay,
A brilliant design is completely worthless if it's not safe and if we can't build it by the thousands. We will make zero compromises here. This is where we follow the official automotive safety playbook to the letter.
And the cornerstone of that playbook is this, ISO 26262, and we are targeting ASIL B. This isn't just a nice-to-have team. This is our non-negotiable ticket to play in the big leagues, especially in Europe. It forces us to design a second, totally independent monitoring system inside the controller that does one job: prevent catastrophic failures, like the car suddenly accelerating on its own. Safety is not an afterthought. It's designed in from day one. And how will we prove all this? By following the V model development process religiously. We start purely in simulation, testing the algorithms and the code. Then we test the real-life controller against a simulated car. Only after that passes do we hook it up to a real motor on a test bench. And finally, we put it in a real vehicle for on-road validation. Every single step validates the one before it. We take no shortcuts.
So, all of this strategic analysis, all these decisions, it all boils down to this, your final engineering checklist. These are the go, no-go decision points for our MCU. This is your mission brief.
So, here it is, our blueprint, our statement of requirements. 96 volts for that performance and supply chain sweet spot. Power output up to 30 kilowatts peak to cover our target markets. A power stage built with discrete MOSFETs for the best cost and scalability. A bomb-proof resolver for motor position sensing. Future-proof communications with CAN FD readiness. And that foundational ASIL B safety target. This is the product we are going to build.
To put it simply, we've looked at global regulations, we've analyzed competitive pressures, and we've faced supply chain realities head-on. And what we've created isn't just a component. What we've designed here today is a strategic platform for this company's future growth. This is the blueprint. The strategy is set. The path forward is crystal clear. So my only question left is for you. Is our team ready to execute?